Good morning. I'm Dr. Jerlin, Professor, Department of Civil Engineering, St. Xavier's Catholic College of Engineering, Nagarkoil. In this video, we'll see how to analyze a beam using slope deflection method. So let us see the introduction about the slope deflection method. Slope deflection method is developed by Professor Jerlin in 1915. This is one of the method of analysis of indeterminate structure, that is continuous beam and strain. By this method, we can find the unknowns like slope and deflection, and using that slope and deflection, we can find the bending moment and shear force. Now we'll see the step-by-step procedure for analyzing a beam using slope deflection method. The first step is fixed end moment. As the name specifies, we have to consider each member separately and fix the ends, then apply the load. Then we have to find the fixed end moment. Okay, in case of a concentrated load, which is acting at the center of the span, the left side fixed end moment is MFAB is equal to minus WL by 8. Right side fixed end moment, MFBA is equal to plus WL by 8. In case of concentrated load, eccentrically placed, that means the load is acting at a distance A from left support and B from right support. The left end fixed end moment is minus W A B square by L square. The right end fixed end moment is plus W A square B by L square. In case of UDL, which is acting over the entire span, the fixed end moment on left side it is minus WL square by 12. Right end it is plus WL square by 12. In case of moment, clockwise moment, acting at the center of the span, the left and right end fixed end moment is plus m by 4. If it is anti-clockwise moment, that is minus m by 4. Then a clockwise moment, which is acting at eccentrically placed. That means at A distance from the left end and B distance from the right end. The fixed end moment left side is m into b into 2a minus b by L square, and right end is plus m into a into 2b minus a by L square. Now we'll see the second step, slope deflection equation. Okay, so for that we have to consider each member and we need to write the slope deflection equation. For each member, there will be two slope deflection equations because each member consists of two ends. So two end moments we have to find. So for each member, two slope deflection equation will be there. Okay, so we'll consider member AB. MAB is equal to MFAB plus 2EI by L into 2 times theta A plus 1 time theta B plus 3 delta by L. Okay, here theta A, 2 times theta A. We are finding moment at A point for AB member. So for the first point, we have to use 2 times slope and the second joint 1 times slope. Okay, so here theta A, theta B are the slope at A point and slope at B. Delta is the deflection. L is the span of the member. E Young's modulus, I moment of inertia. M of AB means fixed end moment for AB member. Okay. Now MBA, the second end, B point, moment at B point for BA member. MBA is equal to M of BA plus 2EI by L into 2 times theta B. For the first joint, we have to use 2 times slope, 2 times theta B plus second joint A, 1 time theta A plus 3 delta by L. Okay, so this is the slope deflection equation. Now the step 3, equilibrium equation. Okay, there are two slope equilibrium equations. The first one is summation of moment at each junction is equal to 0. Okay, summation of moment at junction is equal to 0. Right? So a junction is nothing but at least two members connected at a point means that is called junction. So summation of junction, moment at junction is equal to 0. That is one equilibrium equation. The second equilibrium equation is if the extreme end simply supported, that is roller or hinge support means the moment at that point 0. Right? These are the two equilibrium equations. Okay. Then we can solve the equilibrium equation. We can find the unknown slope and deflection. Then the fourth step, final moment. Okay, our aim is to find the end moments. So in the third step, we'll get the slope and deflection by solving the equilibrium equation. Here, that slope and deflection should be substituted in the second step. What is the second step? That is slope deflection equation. So in the slope deflection equation, we have to substitute the slope and deflection value, and we can find the end moment. That is MAB, MBA, MBC, MCB, and so on. Now we'll analyze one continuous beam using slope deflection method. So first let us read the question. Analyze the continuous beam loaded as shown in figure using slope deflection method. Support B sinks by 10 mm. Sinks is nothing but settlement. Support B settles by 10 mm. Take E is equal to 2 into 10 power 5 Newton per mm square. That is Young's modulus. I, moment of inertia, is equal to 16 into 10 power 7 mm power 4. Sketch the bending moment diagram. Okay, so we have to analyze the continuous beam. That itself, we need to find the bending moment, right? At the end, we have to draw the bending moment diagram also. A continuous beam is given A, B, C, D, right? Here A is fixed and D is also fixed. B and C are continuous. Okay. AB consists of UDL of 20 kilonewton per meter and the span of AB is 6 meter. BC also subjected to UDL of 20 kilonewton per meter and the span of BC is 3 meter. And the CD member consists of a constant rated load 50 kilonewton, which is acting at the center. The span of CD is 6 meter. Therefore, it is 3 meter on either support. Okay. And another value is given. The moment of inertia, I value is same. That means the size of the member is same for all the three members. Okay. Right. Now we have to analyze this continuous beam using slope deflection method. Okay. So let us apply the first step. Before that, here the support A and support D are fixed. Right? Support A and D are fixed. At fixed support, slope value and deflection value is 0. Okay, at fixed support, slope and deflection 0. Therefore, theta A is equal to 0. Similarly, D also fixed. Therefore, theta D is also equal to 0. And in this problem, the support B settles by 10 mm. Okay, settlement is given. That is, delta is given at support B. The effect will be on BA member and BC member. Okay, right. Now we'll apply the first step, fixed end moment. Right. So for that, we have to consider each member separately, apply the load, fix both the ends, and apply the formula. Right. So let us consider AB member. AB member has a span of 6 meter. Right. Fix both the ends. Now apply the load UDL 20 kilonewton per meter over the NGS span, right? So what is the fixed end moment formula for UDL? In case of UDL, fixed end moment M of AB is equal to left side it is minus W L square by 12. Right side M of B is equal to plus W L square by 12. Here W is UDL 20 kilonewton per meter. L is span that is 6 meter. So substitute that value. You get M of AB is minus 60 kilonewton meter and M of BA is plus 60 kilonewton meter. Okay. Now consider next member BC. Fix both the end. What is the span of this BC? 3 meter. The load is UDL, which is 20 kilonewton per meter. Okay, same type of load, but the length is different. Okay, so M of BC is left end minus WL square by 12, right end M of CB is equal to plus WL square by 12. W is 20 kilonewton per meter. Here L is equal to 3 meters. BC member has a span of 3 meters. So substitute those values, you will get M of BC is minus 15 kilonewton meter, M of CB is plus 15 kilonewton meter. Now consider next member, that is CD. Okay, fix both the end, apply the load 50 kilonewton, a constant rate of load at center, right? The span of this beam is 6 meter. Okay, so 3 meter on both the sides. A constant rate to load acting at the center, the fixed end moment formula, left end minus WL by 8, right end plus WL by 8. Okay, here W is 50 kilonewton, L is 6 meter. It is not 3 meter. Okay, the span is 6 meter. So substitute those values. We'll get M of CD is minus 37.5 kilonewton meter and M of DC is plus 37.5 kilonewton meter. Now, the step 2 slope deflection equation. We know that for each member, we'll get two slope deflection equation, right? So let us consider AB member, right? A is fixed and B is intermediate, okay? Right. So, and here in the problem, it is mentioned that support B settles by 10 mm downward, okay? Settles down by 10 mm or sinks down by 10 mm, okay? So you draw the settlement at B point using dotted line. A is fixed. So fixed end slope is 0. Okay. So now draw the deflected shape. Okay. Now you'll get, you see the deflected shape from left to right. That means A to B. Okay. Deflected, see the deflected structure from left to right. So your deflected shape goes downward, right? Then your delta value is negative. Okay, that means in other words, the right side end settles down means delta value is negative. Okay, right support settles downward, delta is negative. Okay, or in other words, you have to draw the deflected shape. See the deflected shape from left to right. The deflected shape goes downward, delta is negative. Right? So here the deflection shape goes downward. So your delta is minus 10 mm. Therefore, delta delta AB is equal to minus 10. Okay, now write the deflected slope deflection equation. MAB is equal to MFAB plus 2EI by L into 2 times theta A plus 1 time theta B plus 3 delta by L. Okay, as we know that theta A is equal to 0 because it is fixed, right? So fixed end, slope and deflection 0. For hinged and roller end, slope is not equal to 0, but deflection 0, right? Slope is not equal to 0 for hinged and roller end. Similarly, the intermediate support also slope is not equal to 0. Okay, here A is the fixed end, extreme end, so slope 0. B is the intermediate support, intermediate support. Therefore, theta B is not equal to 0. That is unknown, one of the unknown. Okay, so now M of AB is minus 60 kilonewton meter plus 2EI by L. L value is 6 meter into 2 times theta A. Theta A value is 0 plus theta B plus 3 delta by L. Delta value is minus 10 mm. So substitute here, right? Divided by L. L is 6 meter, but delta is in terms of mm. L is in terms of meters. So we have to convert in mm. Okay, so 6 meter is equal to 6,000 mm. 1 meter is 1000 mm. Therefore, 6 meter is equal to 6,000 mm. Substitute that, we'll get the equation MAB is equal to minus 60 plus 0.33 EI theta B minus 0.0017 EI. This is your first equation. Now for MBA.